Okay, let's dive right into this explainer. For millennia, we've looked up at the night sky, and honestly, we've projected all kinds of strange behaviors and mythological powers onto the moon. But when you strip away all that folklore and just look at the hard scientific data, the true story of how our nearest celestial neighbor actually shaped Earth's evolutionary history and our climate, well, it's way more bizarre and a lot more fiercely debated than most of us ever realize.
I mean, looking at that distant rock, you really have to ask yourself a fascinating question. What would actually happen to life on Earth if it just vanished? See, our moon is incredibly unique in the solar system. It's a quarter the size of Earth. That is unusually large for a satellite. And it formed about 4.5 billion years ago when a Mars-sized planet named Theia completely smashed into the young Earth. Because it's been orbiting us for almost the entire existence of our planet, it has fundamentally engineered the biological and physical rhythms of our home.
So the crucial point here is that the moon acts as both a compass and a clock for wildlife, literally shaping evolutionary history in three very distinct ways, through time, light, and tide. It is almost impossible to overstate just how deeply ingrained the lunar cycle is in the DNA of life on Earth. From migration to navigation to reproduction, biology is just intimately linked to the moon's movements. Let's actually break down how this plays out in the wild. Take the tides, for example. The moon's gravity drives them. Without that gravitational pull, our tides would be just a third of their current size, driven purely by the distant sun. And because of the extreme wave-battered environments created by these huge tidal ranges, organisms were forced to adapt in some pretty radical ways. Coastal limpets are a perfect example. To survive in these hostile intertidal zones, these mollusks evolved a tongue-like structure covered in scraping teeth that are made of the absolute strongest biological material ever tested. We're talking 5 times stronger than spider silk, and even tougher than man-made Kevlar. Just incredible. And when it comes to lunar light, the adaptations are honestly just as wild. Get this. African dung beetles actually use polarized moonlight to navigate a direct getaway from predators. Sunlight, sure, it creates polarization patterns 100 million times brighter, but at night, the moon completely overwhelms all other natural light. Sunlight reflecting off the moon scatters in our atmosphere, and these beetles can actually detect that specific polarization pattern. Without moonlight, researchers found they just roll their dung balls along random, chaotic paths, completely vulnerable to competitors. Then there's the element of time. Billions of coral polyps actually time their massive underwater snowstorm-like spawning using the lunar cycle as an incredibly precise clock. A circle-lunar clock, to be exact. Now, while things like temperature and salinity do play a role, the actual trigger for the Great Barrier Reef's mass spawning, which is an event so massive you can see it from space, happens annually just after a full moon, right on schedule. But we've got to look beyond biology here, into planetary physics. Going back billions of years ago, a single day on Earth lasted just 10 hours. It was lunar tidal friction that gradually slowed our rotation down. Because the moon is tidally locked to Earth, its gravity drags on our oceans, causing this friction. It basically acts like a massive planetary brake. During the age of the dinosaurs, a day was 22 hours long. If we didn't have this braking motion from our large moon, Earth might be spinning so fast today that our days would only be about 6 hours long. Imagine that. That would radically alter atmospheric turbulence and, well, evolution itself. Now let's see how this builds, because this braking motion ties directly into our planetary mechanics. You see, the slight tilt of our planet is exactly what gives us our predictable, life-giving seasons. As Earth spins, it's not perfectly upright, right? It sits on a tilt, currently at 23.4 degrees relative to our orbital plane. Over a roughly 41,000-year cycle, this tilt gently fluctuates between 22.1 and 24.5 degrees. The scientific term for this planetary tilt is obliquity. And what's really interesting here is that obliquity is the key to keeping our climate stable. Higher obliquity means super extreme summers and winters, while lower obliquity means milder seasons. Because our obliquity operates within such an incredibly tight, narrow 2.4-degree band, our global climate remains relatively stable. And that stability is exactly what has allowed human civilization to completely thrive since the last ice age. But here's where it gets dynamic. Just like a spinning top wobbling on a table, the gravitational tug-of-war from the sun and the moon causes Earth's axis to slowly wobble over a 26,000-year cycle. Because Earth isn't perfectly spherical, it bulges just a little bit at the equator. The sun and the moon exert a torque on this bulge. This creates a slow, conical motion known as the precession of the equinoxes. Basically, it means our North Pole doesn't always point to Polaris. 5,000 years ago, it actually pointed to a star in the constellation Draco. So for decades, the absolute established scientific dogma was Jacques Lascar's 1993 theory. He proposed that the moon was our ultimate climate savior, keeping this wobble completely in check. Lascar calculated that if you mathematically remove the moon, planetary perturbations from other planets would actually resonate with Earth's wobble, causing our obliquity to swing wildly. We're talking potentially between 0 and 85 degrees. This gave rise to this widespread belief in the astrobiology community that you absolutely needed a massive moon to maintain a habitable climate and support advanced life.
But here is the scientific plot twist we've been building up to. Modern 2013 research completely challenges our understanding of the moon's role in our survival. As computational models just grew vastly more sophisticated, two separate researchers, Jack Lissauer and David Waltham, decided to rerun the numbers on a moonless Earth. And what they found? It absolutely shattered a 2-decade-old scientific consensus.
Jack Lissauer's research proved that even without a moon, Earth's tilt would actually remain remarkably stable for hundreds of millions of years. Using a modified orbital integrator, his team found that while the obliquity would vary a bit faster over 100,000-year timescales, it would stay tightly constrained between 20 and 25 degrees. In their models, Earth never reached those chaotic 85-degree death swings Lascar predicted. So this essentially means a large moon is not a strict prerequisite for habitable, Earth-like exoplanets. And David Waltham went even further. He argued that a massive moon like ours creates so much tidal drag that it actively pushes a planet toward instability over time. Remember that planetary break we talked about? Well, Waltham pointed out that while a large moon initially increases the precession frequency, which keeps it away from those dangerous resonances, its massive tidal drag slows the planet's rotation down over billions of years. This slowing rotation inevitably reduces the precession rate, accelerating the entire system right back toward those dangerous chaotic resonances. It's crazy.
When you really look at this hard data, it reveals that rather than saving us, our Earth-Moon system is actually hovering right on the very edge of chaotic instability today. Waltham's modeling showed that after 4.5 billion years of evolution, systems with exceptionally large moons are fundamentally unstable. The incredible paradox here is that our moon didn't ensure permanent stability. It very nearly destroyed it.
To put that into perspective, if the moon were just 9% more massive, our Earth's tilt would have eventually become unstable, completely throwing our climate into utter chaos. Alternately, if the Earth-Moon system had just 8% less angular momentum following that ancient collision with Theia, we would be unstable right now. We didn't get a perfect climate savior, we got an incredibly lucky near miss.
So what does this all actually mean for us? Well, Waltham speculates that the moon's real gift might simply be slowing our spin just enough to make our ice ages rare and mild. Earth might be unique precisely because it threaded the needle. We have a moon just large enough to slow our rotation to a beautiful 24-hour day, minimizing those extreme temperature contrasts between the equator and the poles. And because we're hovering right on the edge of instability, our climate cycles are slow. This gives biology the vital time it needs to adapt to the mild ice ages that do occur.
I'll leave you with this to ponder. If our nearest neighbor isn't the climate savior we always thought it was, is its greatest legacy simply giving us the beautiful, steady rhythm of our days? From the limpets clinging to the rocks, to the dung beetles navigating by its polarized light, to the very rotation of the ground beneath our feet, the moon really is the quiet conductor of Earth's biological and physical symphony. Thanks for joining me for this explainer, and keep looking up.